Hello, my name is Alan Harris. This is my final presentation for ME 569, Mechanical Behavior of Materials. My project topic is the fatigue analysis of ANSYS of the final length of a simple robotic arm, as well as demonstrating how even a small change can drastically increase lifespan. The arm is quite simple. It is mainly designed for the experience of using ANSYS to perform a finite element analysis on a shape that would be incredibly complex to do by hand. Here, you can see the basic geometry of my parts. Up here on the left, you can see the two robotic manipulators, this arc and this arc respectively. This raised area represents an object that they are grabbing and provides a great place for forces to be applied for analysis. Here, off on the top right, you can see a hollow cylinder bored into the arm. This is where the rest of the robotic arm would be connected, and presumably torque would be applied. Here, on the bottom, you can see the back view of the part. Instead of being solid, the arm has 4 rectangles cut through most of it, excluding the front of the part and the cylinder for mounting. This was done because the stresses on the part in no way require a completely solid bar. Now, there are 2 models being used in this analysis. The first is Model A. It's a pretty standard part. Things to note is that here there is a 90-degree angle, giving it a fairly sharp corner, and although this angle itself is also fairly sharp, it is not quite 90 degrees. These are mirrored. This angle here has a cousin right here, much like the one here has one here, both hidden behind the model. Model B, on those same places, there are the changes. Here, the sharp corner has been replaced with a round, much like on this side, and the remaining 2 formerly sharp edges here and here. This was done because of an effect called edge concentration. Whenever you have an edge on a part that's being tested, the force there will affect the part as if multiplied by a factor which depends on the local geometry. Generally, we have to access a number of tables and charts in order to figure out what exactly this multiplication factor would be. Here you can see the boundary conditions of the initial stress test. The initial stress test isn't meant to be an exhaustive analysis. It's merely meant to put a very large force on the part in order to magnify any potential issues. So first, we have condition A here, standard Earth gravity for the parts. Next, we have condition B, a force of 5,000 newtons on the piece being held by the two robotic manipulators. Finally, we have condition C. Condition C is a fixed support where, in order to represent how the robotic arm will be connected to other arms. Moving on. This is a general deformation of This is the general deformation of the robotic arm. As you can see, the front of it is the most deflected, as that is where the force is applying, whereas the fixed support doesn't move at all. This doesn't change regardless of how we change the loads. The bending is magnified to be visible across all of the analysis, no matter how small it is, and the colors remain the same even if the magnitudes they represent change. Thus, we will only have this one image of deformation. Next, we have a picture of the general stress concentrations in the parts. As you can see, there's a good amount of stress here where the fixed support is, as well, which is mirrored on the bottom. Next, there's a good amount of support in these corners where the robotic manipulators are attached. This is where my analysis will focus, because these parts have, across all the analysis, have a more focused stress. They get more force per square inch, and they break first. Now, this is the fatigue life for 5 kilonewton fully reversed stress. That is, it goes from 0 to 5,000 newtons, then to negative 5,000 newtons, and back to 0, and that represents a single cycle. For Model A, you can see that the part lasts for only 624 cycles, with the critical part being right here and here. This is where it first breaks, and it is exactly at the edges that were later moved away in Model B. As you can see, the shortest life is instead spread out by a good amount, still here and here where the edges used to be, but those places now survive up to 819 cycles, a number which is 25% greater than Model A, all for the low cost of adding a few cubic millimeters of material to the parts. The next stage was changing the analysis from having a mean stress 0, that is fully reversed force from negative 5,000 to 5,000, to having a mean stress equal to half the applied force. In addition, the load was changed from a 5,000 Newton force to a 6 megapascal pressure to more accurately represent potential real-life loads. Under this pressure, we can see that the highest concentration of pressure in the Model A still occurs at these corners, though again it's in a very small area comparatively, at 209 megapascals. Whereas in Model B, the force concentration is still very great, but is only at 187 megapascals, which, despite being only a 5% change, made a great change in how their lifespans worked. In addition, just for context, each of these cycles only moves the bar roughly 1.5 millimeters up from its resting position. Now, Model A can be moved that 1.5 millimeters at a minimum, at the worst, right here, of course, 107,000 times. Which is a not terrible life for a part, though again depends on the application. Model B, however, once more spreads out the damage, but will survive for up to 173,000 cycles, being moved up and down that 1.5 millimeters. So in this gentler test than the initial stress test, the part survives a full 70% longer than it would without that very small amount of rounding placed into it. Even if adding those rounds made the part cost 50% more, this 70% increase in life would be well worth it. And from what I understand about manufacturing, adding those rounds with their internal would cost much less than the rest of the parts. Overall, I hope this presentation has helped clarify how important keeping edges out of the critical locations on your parts can be. Thank you for your time.